Hi, my name is Lindsey Druschel, and my partner's name is Stephanie Browning, and this semester we worked on a vagus nerve stimulation model. Vagus nerve stimulation is an up-and-coming treatment for epilepsy and depression. It consists of implanting a copper electrode around the cervical vagus nerve in the neck and stimulating it to regulate brain activity. However, currently vagus nerve stimulation results are very variable between patients, with a large number experiencing adverse side effects. There is currently little known about the spatial organization of the vagus nerve, such as how the fibers will be bundled and if certain regions stimulate specific parts of the body. The vagus nerve axons are bundled into fascicles, which have been found to split or merge within each other every 560 microns. This video shows the splitting and merging of the fascicles within a few centimeters of the cervical vagus nerve. The stimulation window where a surgeon might implant this cuff electrode is also several centimeters long. So this video shows all the different regions where the electrode could be placed. Due to variability, the surgeon will not know how many fascicles are within the region he's stimulating. So there could be anywhere between 1 to over 10 fascicles, and we wanted to investigate if the number of fascicles would impact the stimulation. As I previously mentioned, vagus nerve stimulation is typically performed with the cuff electrode that will wrap around the length of the nerve. For this model, we used an insulating polyimide cuff with a platinum electrode contact underneath. The nerve has a diameter of 5.1 millimeters and the cuff has a length of 2.5 millimeters, which is consistent with the dimensions of human subjects. Shown here is our 7-fascicle model, and we also constructed a 2-fascicle model. Within the cross-section, you can see the different components within each nerve. Each fascicle contains an endoneurium, which is the location of the axons, the perineurium, which lines the endoneurium to create the individual fascicles, and the epineurium, which is a tissue making up the rest of the nerve outside of the fascicles. The most important distinction in the properties of these 3 regions is that the perineurium has a resistivity that is 40 times higher than the endoneurium and epineurium, which is going to keep current from entering the fascicle. Therefore, in comparing our 2 and 7-fascicle models, we expect the 7-fascicle model to have more overall perineurium, which will increase the nerve stimulation threshold. In COMSOL, we built our 2 nerve models to represent different possible anatomical structures that could be stimulated in the cervical region. We made the nerve 5 centimeters long, then we added our cuff electrode 1 centimeter down the length. In this model, we're using cathodic stimulation and a 0.25 millisecond pulse width in accordance with vagus nerve stimulation studies. We generated the voltage fields and then took a line down the center of each fascicle along the length of the nerve, then exported the voltage values to see what the extracellular potentials would be for an axon in that location. Fascicle 1 in both models is the same size and in the same position, so that we could directly compare the effects. From the voltage fields alone, there's no visible difference between the 2, so we went to MATLAB and Neuron to examine the model in more depth.
Second difference plots were generated for each fascicle's electric potentials. The second difference, also known as the activating function, will show the excitability of the axon based on the extracellular field. The 7-fascicle model had larger second difference magnitudes overall, but we believe this is because smaller fascicles have a thinner perineurium and a shorter distance to the center of the fascicle, making them easier to activate. When comparing the results of the same fascicle, fascicle number 1, under both conditions, we see that the second difference in fascicle number 1 of the 7-fascicle model increased by about 4% compared to the 2-fascicle model, showing that the additional fascicles decreased its excitability. Using MATLAB, we interpolated the electrical potential data from COMSOL to fit a 200-segment axon, which we simulated in Neuron. Each fascicle was stimulated at different current settings until some fascicles failed to reach an action potential. All fascicles reached action potential at 0.2 milliamps. At 0.1 milliamp, fascicles 2, 3, 4, 6, and 7 in the 7-fascicle model reached action potential, but fascicles 1 and 5 did not. Even though fascicle 5 is a thinner fascicle, it is near the center of the nerve and is shielded from the electrode cuff by the fascicles surrounding it, and we believe its position in the nerve is why it had a higher stimulation threshold. Neither fascicle in the 2-fascicle model reached action potential at 0.1 milliamps. In conclusion, the number of fascicles in a nerve can lead to differences in action potential stimulation. The splitting and merging of fascicles in the vagus nerve should be accounted for when placing an electrode cuff and when setting stimulation parameters. Failure to account for the number, size, and position of fascicles in the vagus nerve could lead to over or under stimulation. This concludes our presentation, and thank you for watching.